laser pointer here.
Yeah, okay, I have one.
Oh, you have it on?
Yeah. Okay, fine. And the clicker, this works?
One is for bad questions.
Yeah. Okay, thank you very much, Alfred. Thanks for staying on till the end for this session. I'm going to talk on the theme of sustainable production of fuels and chemicals. And by sustainable, I mean energy input from the sun, one way or another. And as illustrated to the right in this schematic here, it can happen in a photochemical process. You can make electricity, and you can have an electrochemical process, or you can use biomass, as we just heard about. But one way or another, we need to get these things to function, to make those fuels and base chemicals that I'm showing in the lower right corner. For this talk, I'll focus on just one of these molecules, namely ammonia. And before I move on, let me just point out that this is a collaboration between my theoretical group and then 3 experimental groups, one by Matteo Cagnello, the other one by Tom Jaramillo, and the last one, Anders Nilsson, who you'll hear tomorrow. And I've also actually shown in italics here those people who did the work that I'm going to talk about. So why worry about ammonia? Well, for one thing, it provides most of the fertilizer that we use today. And the importance cannot be exaggerated, and that's illustrated in the plot to the right, which shows that the development in the world population and our ability to produce ammonia are closely correlated. Another way of saying this is that most of us wouldn't be here today had it not been for this one invention by Haber-Bosch to make more fertilizers. That's what you can see here. So that's one aspect, and let me just point out that it is directly related to energy in the sense that about 1% of all energy in the world is being used on this one single chemical process. But there's actually another interesting aspect which is illustrated here to the right, to the left, namely that the energy content in ammonia is very high. It's comparable to methanol, not quite as high as gasoline, but much higher than, say, compressed hydrogen gas or batteries, which you have down in the lower left corner there. So one possibility would be to use ammonia as a fuel, and you can run an auto engine on ammonia or diesel engine, no problem. You could imagine a nitrogen cycle, as illustrated to the right there, where you have nitrogen in the atmosphere, you have nitrogen reduction to ammonia, you use the ammonia as a fuel in combustion and so on. And the nice thing here is that unlike CO2, N2 actually you have 80%, so the capture problem is a much smaller one. The main problem we have, of course, is that ammonia is poisonous, so we need a safe way of storing it. But there are actually ways like that, for instance, in methylamine salts. So for this talk, I'll focus on one of these ways of getting to ammonia, namely by electrocatalysis. And the reason is the following. There's been a fantastic development in the last few years when it comes to the price of electricity coming from sustainable sources. So these are data from Lazard showing to the left the price of electricity from wind farms, and to the right from solar photovoltaics. And in both cases, they have crossed the price from a modern natural gas plant. If you were to look at coal, it's much, much higher up. So we are actually getting to a point where electricity from sustainable sources is competitive or even better than what you have from fossil resources. The problem is, of course, that it's intermittent. So we need a way to store it, and of course, one way of doing that is exactly by using it to make fuels or chemicals. There's another aspect of this which I think is potentially important, namely that when you have your energy distributed, then in principle, there's no reason why you should have centralized production of various chemicals and fuels. So what I'm showing to the right is on the top is a conventional ammonia plant. There are very few of those in the world because they are enormous installations sitting on top of a lot of natural gas. But you could imagine, if the energy source is photovoltaic, that you actually did it, as illustrated in the lower right corner, by having a little electrolysis cell, splitting water and using the protons to produce N2, and then you make it actually close to the field. And you only make a little bit at a time and use that, and you get rid of all of the runoff problems and the other problems that we have with the current use of fertilizer. It's a possibility. So I think the fact that energy will become distributed opens up for a lot of possibilities. And let me just point to one aspect. I've listed a number here to the left, but the lower one, namely that instead of building billion-dollar scale facilities, you will be a few $1,000s. And that, of course, will help financing if you want to build something in Nigeria, for instance, but it will also help innovation. So the chemical industry is incredibly conservative, and for a good reason, right? If you have invested $5 billion in a production facility, you need to use that. So if somebody comes with a better technology, you're not going to adopt it, because you first have to pay off what you have invested. But if you have much smaller plants, we could see a pace of innovation that could go up drastically. So if we want to reduce N2 electrochemically, there are a number of options, and let me just focus here on two of them. One is that you first electrochemically make hydrogen, and then you use that hydrogen in a thermal reactor, like Haber-Bosch, but it should be at low temperature and pressure. I'll get back to that in a moment. And the other alternative is, of course, that we do it directly by reducing N2 electrochemically, and this is basically what nitrogenase, the natural enzyme that does this, that's the way that happens. So let me look at each of these processes one after the other and say a little bit about what are the challenges here. So first, making hydrogen, that is reducing protons by combining protons and electrons to form H2. This is an old problem we have known for decades, or actually centuries, that platinum group metals are very good catalysts for this. And this is illustrated to the left, top left here. If you look at rates, measured rates, as a function of one descriptor of catalytic activity, then at the top of this volcano relationship, you find platinum, rhenium, palladium, all the expensive and rare metals. And we would dearly like to have something that was much less expensive. And one possibility that has come out of recent research, theoretical and experimental, is that, for instance, something like molybdenum disulfide, a much cheaper material, is not as good, not nearly as good as platinum, but it's cheap, and you can nanostructure materials to expose a lot of these cheap active sites. And that's what, for instance, has happened to a large extent in the group of Tom Jaramillo, but many groups have contributed. And the result you see over there to the right, if you look at the overpotential, that is the extra price we pay for making hydrogen using other catalysts than platinum, then you see that has, or platinum group metals, then that has really gone down tremendously over the last 5 years or so. And this is really a success for a scientific approach to trying to solve some of these problems. We are still not there because the individual active site is not as good as that of platinum. We'll never get there. That's the dashed line at the bottom here. But we are actually being able to engineer nanostructure materials to solve that problem. Now, let's then, if you make the hydrogen by electrolysis, then you have the hydrogen at low temperature and low pressure. And then you would really like not to have to go to very high temperatures and pressures to make ammonia. So this is back now to the Haber-Bosch process. I'm showing again here a typical Haber-Bosch plant. It has a large hydrogen plant, and then the conversion of nitrogen to ammonia happens at 100, 150 bar, high temperatures, and that is needed. We understand this very, very well. We know why ruthenium is the best catalyst, as shown to the right. Iron is being used not because it's the best, but because it's dirt cheap. And so this is known technology. And let me just spend 1 minute explaining why you need this high temperature and pressure to do this. And the way that, as a theorist, you describe this is by looking at the free energy diagram. So this is simply the free energy barriers and the energies of intermediates for the whole process. So if you follow the black curve there from the left, then first there's the barrier for N2 dissociation. Then there are 3 steps where you dissociate hydrogen, no barrier, it's very easy. And then you have a number of steps where you add hydrogen to the nitrogen, one after the other, and eventually you get 2 ammonias off for each N2 and 3 H2. That's how it looks from a theoretical point of view. And you can see two important things here. One is that you have a big barrier for dissociating the nitrogen. And the other is that you have what is known as a thermodynamic sink. That is, you see this big hole around nitrogen on the surface, and what it really means is that if you try to do this at 300 Kelvin, that's the black one, then you will cover the surface with nitrogen and it will be dead as a brick. It will do nothing for you. To solve the problem, you heat it up. So if we go to 700 Kelvin, then you get to the red curve, and now this thermodynamic sink has disappeared, but now another unpleasant thing has happened, because if you look at the final state, that has a free energy that is higher than the initial state, and that means you don't make any ammonia anymore. So to solve that problem, you increase the pressure. So if black is now the 1 bar that I showed you before, and then if you go to 100 bars, the red curve, then you see that now the final state is lower than the initial state, and that's it. So if we want to lower the pressure, which is really what you need if you want a simple process, you don't want equipment that run at 100, 150 bar out in the barn, I tell you. But then you need to lower the temperature as well. That is what this tells us. And a lower temperature process means that you need to do things better. You need a better catalyst than we have now. And a better catalyst is one where you can lower the barrier, but don't get this deep thermodynamic sink. So it's all about what is the transition state energy for N2 dissociation versus the binding energy of nitrogen on the surface. So why don't we just find a material where that barrier is lower, but you don't bind nitrogen stronger? That's the solution, obviously. And here's why that has failed now for 100 years, finding that material. Because what I'm showing here is the rate, that is a heat map of the rate of ammonia synthesis, shown as a function of those 2 parameters, the transition state energy for N2 dissociation on the y-axis and the adsorption energy of nitrogen on the x-axis. And what you see is the optimum, there is an optimum, but it's way off where all the known catalysts are. And I'm just putting on here sort of some typical metal catalysts, but I can tell you something like 250,000 different materials have been tested as possible catalysts for this reaction. And all of them have been running up and down this line. We have empirical proof of that because nothing has been found. So this is the problem we're up against. We need a new paradigm for creating catalyst materials that can do this. And this is one place where computational methods and theory are actually proving to be something we are applying now, because what we can do on the computer is we can play around much more freely than you can in the laboratory. So let me just show you another version of the same plot. So you have this heat map, you have the best catalyst where it's deep red, and you have all the known metal catalysts up there along this scaling line. And what Ayush Singh and Brian Rohr did was they played around the computer. Could we find something, some structure that could do this much better? And in fact, yes. So if you look now, all of these different symbols here, they represent one possible structure that can do this. And one example is shown to the right. if you have something very reactive, but you only have a diamond, nothing more, then actually you can be way off the scaling line and you should be able to do much better. This now requires that we can actually synthesize and stabilize such structures, and this is what we're working on. But it is possible, but we have to think totally differently about how we make these materials. So let me finally go to the question of what about a more direct electrochemical process, and let me illustrate again here sort of the conceptual outline. You split water on one electrode, and you use the protons and the electrons that come from your solar cell to reduce the N2. And what it means is that you could, in principle, have this run only when the sun is shining and only when there's water present. That is, only when you need it and not when you don't need it. But one question is, what is the amount of energy that you need here? Is that out of the question or not? And if we take the typical amount of fertilizer that is being used on a field in the US, which is definitely too much, let me just say that. But if we just take that as a number, and say we can produce this with a large O potential, 1 volt, then what we need is 5 square meters of solar cell, off-the-shelf solar cell per hectare. Nothing. It is all about actually being able to make this cheaply, and the first step is to find catalysts that can do this. And let me just tell you, we don't have them. Nobody has them, so yet. But that's the challenge. And let me just show you here what the challenge is again. And we can, you've seen one of these before. That was for the thermal process. This is for the electrochemical process. Again, we have a heat map showing where is the best catalyst. That is the deep red. There's sort of a small point there in the middle of this triangle. You may be able to see it. That's where we wanted to be in terms of these two descriptors here. But the point is that, again, all of the known materials, they're way off this scaling line. You cannot vary one of these stabilities without varying the other one, and therefore you don't get where you want to go. So that's one problem. The other problem is illustrated to the right. What I'm showing here is basically what happens when you run up and down this line where all the materials are. So I'm showing this in one dimension now. And the black is basically showing you the potential where you can begin to reduce N2 with a reasonable rate. So for rhenium, for instance, you can see you need something like a potential of minus 0.9 volts. The blue is the same potential, but now for making hydrogen for the same materials. And what you see is that you need a much lower potential, or much higher if you like, but much lower O potential to make hydrogen than to reduce N2. So what happens is, if you stick one of these materials down as an electrode in water, and you try to run it, then you get a lot of hydrogen and absolutely nothing else. And that has been proven. That is the problem. So how do we deal with this? And let me just indicate here where our thinking is going. If you want the mathematics, you can look to the left. Let me just tell you what the problem is. The problem is that at these negative potentials, you have protons, you have electrons in the surface, you get the surface covered with hydrogen. And then when another proton comes in and recombines with an electron, you form H2. That's the problem. What you really want is for nitrogen to sit there and get hit by the protons. So what you need to do is somehow to restrict the access of either protons or electrons or both. Then you can control the selectivity. And what is illustrated to the right here are various ways in which you can do that. And let me just illustrate one. If you look at what is called A here, then it illustrates that if you go to a solvent which is not water, that does not include a lot of protons, then you can actually control the access to protons, and you can get some nitrogen onto the surface. And we're looking, with some success now, we're looking at ways to achieve this right now. But finally, let me point to a totally different way of doing the same thing. So, as I mentioned, the problem is that you make hydrogen instead of reducing the nitrogen. So what about doing the reduction, but in the absence of any protons whatsoever? And one way of doing that is illustrated here. And you can, for instance, take a lithium salt, lithium plus, and reduce that to form metallic lithium. This is what happens at one of the electrodes in any lithium-ion battery when you are charging it. So this is well known. Lithium reacts at room temperature with nitrogen to form lithium nitride. That's step 2. And if you take lithium nitride and you expose it to water, then you make ammonia, again at room temperature, and you get your lithium hydroxide back, and you can put that back into step 1, and you have not a catalytic process, but you have a cycle that can run. And this has been illustrated now. Josh Magini is here. He was the one who did it, and he can answer all the difficult questions in Tom Harmio's group. But you can do this with close to 100% efficiency. So it is actually possible, but you need to find a totally new process. And let me show you how we got this idea. It actually, again, is something where theory plays a role. What is shown here are free energies of various species as a function of the applied potential. And let me just focus on 3 of these lines, the red, the blue, and the green. They're sort of thicker lines. The red is the energy of lithium metal, and the green is that of lithium ions. And you can see at 0 potential, the energy of the lithium metal is way above that of the lithium ion, so you'll never plate it at all. But if you go to something a little over -3 volts, then actually the lithium line goes underneath the lithium ion line, and you can plate out the lithium. Now you can go back to 0 potential, and you can expose it to nitrogen. That takes you from the red to the blue. And then you can expose it to water. That takes you from the blue to the green, and you have the full cycle. Very simple. Now, we need to apply -3 volts. You could ask, is that at all, does that make any sense? So let me just end here by showing you just the cost of this part of the electrochemistry. So what is shown here is basically the cost per ton of ammonia as a function of the amount of the cell voltage you need to run this. And then for different electricity prices, so you can make your own pick here, or you can try to guess where it will be. It is a fact that there are many places in the world where electricity prices are close to 0 now, at least at some times during the day, or night for that matter. And you can also see where's conventional ammonia there. So it is, even with this large O potential, it's actually not totally out of the question that this could become economically viable. I should say there's no capital cost involved here, so you definitely need to be closer to the green than to the red here scenario, that's for sure. But on the other hand, we should not really be comparing to the out-of-gate price of ammonia. We should actually be comparing to the price of ammonia at the farmer. And that is a totally different thing. For instance, ammonia in Central Africa costs 5 times as much as it does in Central US. So you can shift this up by a factor of 5 if you want some places in the world. So let me finish here by making sure that I mention who funded this, DOE and the Willem Foundation, and then just leave up here just leave you with that picture. And thank you for your attention.